But I'm so happy that you guys are here. This is going to be fantastic to review before you even begin your class. And I actually would love to know, did you guys start your class already, or when is it starting? So let us know in the chat. That would be awesome to just see what your schedule is like, any nerves so far. I know that every semester, uh, and I'll introduce you Cooper is, by the way, very soon. But I know that every semester, no matter what, back to school always kind of brought back those nerves, no matter what age, or what like grade you get to, right? And people are saying August 18th, the 19th, perfect. That is typically when most students start school. So wonderful. We have a good group growing here. So why don't we kick this off, start this off? So thank you so much for being here for our Organic Chemistry 2 live tutoring this time. And I can't wait for you guys to meet our newest addition to the community team, Cooper. I'll do a formal introduction in just a second, but I do want to just highlight everything that you have available to you on community and a major thing that I recommend doing before starting your class next week, which I can see most of you are starting then. So I'm gonna go ahead and just share my screen for a second. So as I'm doing this, let's see. There we go. Okay, so of course, if you're new to community, this is your first time with us, this is everything that you see on the catalog page. And this is going to be what's most important for you guys is understanding, okay, what am I working on? If you're doing Organic Chemistry 1 right now, that review, this is what I recommend. I recommend actually going and watching these two videos, especially starting with this first one. That's going to be on the topics that some of the topics we're going to cover today. And those are the ones that I recommend knowing those foundational topics like resonance, acids and bases, stereochemistry, things like that. And then, of course, the other thing that I recommend doing when you guys have time here is watching this one. This is like the holy grail, I would say, because it is reviewing all of the main reactions you learned in OChem 1, which is going to carry on to OChem 2. Unfortunately, I know, but it builds on top of that. So please make sure that you guys know this. I'll put the links and everything in the chat. And of course, the other thing I wanted to mention was just how this was going to work. So this is going to be available for, and by this I mean the weekly live tutoring sessions. The whole idea here is we created an entirely new premium plan, which is why Cooper is here. This is Cooper McIntyre, and he will be the one leading these weekly tutoring sessions. He'll be walking you through different Organic Chemistry 2 topics and just breaking down a lot of those complicated subjects. So how this is essentially going to work is you're going to get access to a private channel on our community page here. And you'll notice that it's actually going to start tomorrow. But what you're going to see is there's going to be a post. And from that post, you can comment whatever questions you guys have. And that's what Cooper is going to choose from to then put on his live tutoring sessions. And on his live tutoring sessions, that's actually what he's going to be answering. So it's based on the questions you guys bring. And again, this is for premium members. For right now, all community members can see this because we want you to understand how this is going to work. And we also really want you to start off the semester right. Like the main thing here is getting ahead, remembering and kind of getting into the groove already of studying even before your class starts. That's going to set you up for success. And that's exactly what we want to help you do. So that's the whole idea here with the premium plan. And of course, we'll be announcing more and more of how everything works and whenever we have our next weekly live tutoring, which for right now will be Mondays and Wednesdays, Wednesday specifically for organic chemistry for this month. So perfect. That's the main idea. And as Cooper gets his setup going, I'm just going to go ahead and put what I mentioned in the chat right now. So this is the review I recommend. And now Cooper is going to introduce himself a bit so you know who he is, and then he'll walk you through this entire session and this review. I do want to mention that I'll still be in the chat. So if you have a question specifically about community, or if I can just quickly answer a question, I'll be there. If it's related to whatever Cooper is going over, he'll look at that and he'll also answer it within the session. So you guys have the opportunity to ask questions. So go ahead, Cooper.
Sweet. Well, first and foremost, everyone can see my screen, correct? Perfect. Alrighty, y'all. So basically, just to kick things off, I do want to introduce myself a bit, just so for those of you who are new, that you guys know who I am. But my name is Cooper. I started Catalyst Chemistry around a year ago, and it's basically my way of just helping all the students I can just excel in organic chemistry, just because I know how tough and intimidating the course could be. But for those of you who are here, I do want to give myself just to introduce myself so that you don't think of me as just some OChem nerd. Basically, just some fun facts about me to kick things off. I love rock climbing, love the outdoors. I try to go rock climbing a whole bunch of times throughout the week, whether it's indoor, outdoors, whatever it may be. And then also, not a lot of people know this about me, but I am a zipline tour guide. So during the weekends, I consider myself, like a tutor of the trees. Absolutely love what I do. And then also, I have an absolutely beautiful one-eyed calico kitty. She's right there. Her name is Sedona, so you guys can just admire her beauty. And then in terms of, my education background, I went to Ohio State, where I got a degree in cellular molecular neuroscience. As you can see, I kind of shifted gears a little bit. I did enjoy OChem a little too much. And then one thing I do want to mention before we dive into the material is that both Melissa and I have been in your shoes. So if you're currently feeling a little, scared about going into organic chemistry too, that's okay. That's normal. We've been there. We weren't born with, the knowledge of organic chemistry. We know it's intimidating, and that's what we're here for, is to try to help you the best we can. But just to dive into everything, this is what we'll be covering in today's session. And we'll go over some stereochemistry topics, going over the types of stereoisomers, whether it's enantiomers, diastereomers, and some other things as well. And then from there, we'll dive into acid-base reactions, just doing a good review of both acid and base strength, just because a lot of those factors of stability will have a huge role.
All right, he'll be right back. I think he's having a little tech issue, but uh, just looking at everything that we're covering, what is the main topic that you guys would say you struggle with the most? If you are looking at this and you're like, oh, is it resonance? I don't really remember resonance. Let me know in the chat because what I've seen has been resonance a lot of times. Uh, there you go. You're back, Cooper. I believe. There you go.
Last talking.
I just mentioned that we're going to dive into resonance. So if you want to
Perfect.
just jump right into stereochemistry, let's knock this out.
Sweet. Yeah, we'll do that. And then as we keep on going, yet again, if you do have any questions, please feel free to put it into the chat and I'll take a look at it when I can. And then before we go over stereochemistry, one thing I do want to mention is that the key to mastering organic chemistry 2 is just making sure you have a solid foundation of those topics from OChem 1. I know you've probably heard that organic chemistry 2 is a lot harder than organic chemistry 1, but honestly, organic chemistry 2 is just a solid, you just apply everything you learned in OChem 1. So you're not necessarily learning anything new. You're just kind of doing a deeper dive into the material. I know you'll probably learn spectroscopy. That will definitely be a new topic. But everything else besides that, especially if you're talking about aromaticity or you're talking about aromatic reactions, at its core, that's just resonance, which is why we'll be doing a deep dive with that today. But to start off with the material, we'll go over stereochemistry first. And here is a nice little chart that I use in terms of my thought process whenever I'm given two different structures and I want to assess the relationship between those two molecules, whether it's seeing that they're enantiomers, diastereomers, or if they're constitutional isomers. And the first thing I ask myself is I want to see if those molecules have the same atom connectivity. Now, if they do not have the same atom connectivity, that means we're looking at constitutional isomers. Now, remember, constitutional isomers will have the same molecular formula but different atom connectivity, as opposed to if our molecules did have the same atom connectivity, meaning all the individual atoms are still being bonded to the same atoms, but they have different spatial orientations, then we're looking at stereoisomers. Now, from stereoisomers, we can branch off a little more. And the next question I want to ask myself is, are those molecules mirror images of each other? And more specifically, another way we can ask that question is seeing if all the configurations in that molecule changed or not. So if the molecules are mirror images, then we are looking at enantiomers. And yet again, enantiomers are when we have all chiral centers changing their configuration, which is how we get the reflection of a molecule. But just say if we're looking at two molecules that are not mirror images, then we're talking about diastereomers, where only some chiral centers changed while the others did not. So we'll go ahead and use that reasoning with our first example right here. So for these next list of structures, we want to determine the relationship between the molecules, and they can either be enantiomers, diastereomers, identical, or they can be constitutional isomers. So if we're looking at these two molecules, the first thing that catches my eye is the wedged and dashed notation. So if we look at the left molecule, which I'll go ahead and designate which is which, if we look at the left molecule, we currently have a wedged hydrogen, but if we move over to the right molecule, we also have a wedged hydrogen. And then also another thing that I'm noticing are these ethyl groups. They're currently facing towards each other. So since they're facing towards each other, I have a thought that they might be mirror images. And one of the ways we can go ahead and confirm that they are mirror images is by just drawing in a mirror plane. Perfect. So for mirror images, just to do a recap in terms of what those are, a common example is your left and your right hand. Now, these are what are called enantiomers, where yet again, they are mirror images only because they are a perfect reflection of each other. Our pinkies are on the same side and our thumbs are on the same side. So that's a good example of what a mirror image is and how we'll be applying it to this concept in this example. But currently, our ethyl group on our left molecule is facing towards our mirror plane, and then this ethyl group as well is facing towards our mirror, and then our methyl groups are facing away from them. And since our wedged and dashed notation on both molecules align with each other, that means they are mirror images. So since they are mirror images, that means we're dealing with enantiomers. Now, another way we can go through and solve this question is by actually flipping the molecule over. And what we can do is align our methyl groups together along with our ethyl groups. Now, what I mean by flipping the molecule is I'm referring to like turning the page of a book, right? So it's kind of like you're flipping your hand over to where this methyl group will be on the left side, and then this ethyl group will move over towards the right side. So we'll go through and draw that flip. Where yet again, methyl is now on the left, ethyl is now on the right. But here's where things can get tricky. What happens to the wedged and dash notation? Since we're flipping something over like a book, that means we have to flip the notation. So for example, if we're looking at the alcohol, it's facing away from us since it is in the dash notation, but after we flip it, it will now face towards us, meaning it'll be wedged. And then same with that hydrogen. It was facing towards us in this molecule up here, or sorry, that conformer or side of the molecule, it's facing towards us. but after we flip it, the hydrogen will face away from us. And then just to show you guys what that actually looks like, I know this molecule is not the exact same one, but we can think of the white group right here as our methyl group, and then this larger group over here is our ethyl group, and then this red group over here is our alcohol. As we can see, the alcohol from your perspective is currently dashed as it's facing away from you, but after we flip it, you see how we change the locations of those groups, the white and then this larger group over here. But after flipping it, that alcohol is now facing towards you. And that's exactly what we're doing with this flip on paper. And then what we can also do is drag and drop that molecule and just assess how the wedges and dashes look against each other. So our methyls perfectly align, our ethyls perfectly align, but if we look at those wedges and dashes, our hydrogen is dashed right here, but it is actually wedged up top. And then same with that alcohol, wedged down here, dashed on top. So we can see that those molecules, if you remember, are what are called non-superimposable, meaning that if we were to take the molecules, you cannot perfectly overlay them on each other. Same idea with your left and right hand. They're mirror images of each other, but if you had your palms facing the exact same direction, you can see how they're not perfectly aligned. Sweet. From there, we'll go through and we'll look at our next example. So for this one, what we can do is, yet again, we can see if they are mirror images. So we'll go ahead and include our mirror plane. And by doing that, we can see our bromines are reflections, our methyl groups are reflections. But if we were to look at the alcohol, we see that they are not reflections of each other, as our left alcohol is currently dashed, and then our right alcohol is currently wedged. So just by it not being a mirror image, and my thought process is telling me that it may be a diastereomer. And then just to clarify that, what we can do is we can yet again flip this molecule so that our, for example, methyl groups are aligned. And then same with the bromine and our alcohol. And yet again, all we're doing is we're flipping it over like we're turning the page of a book. So if we go through, we'll draw it out. Move this over. So by flipping it, we're moving this methyl group. It'll now be on the left side. But since we're turning it over like a book, what was facing towards us now faces away from us. And then yet again, same with that alcohol. Since we're turning it over, it was wedged right here, but it will now be dashed. And then same with that bromine. It was dashed, but after flipping it, it'll now be wedged. So what we can do is we'll go ahead and drag this molecule over and we'll see the differences in those wedges and dashes. So let's look at this methyl group first. We'll go through and highlight them. Our methyl groups ended up flipping. There we go. Our methyl group flipped. And then let's look at our bromine. Our bromine was wedged right there. But then after turning our molecule over, we can see that it is now dashed. And then here's the main indicator that we're dealing with diastereomers is our alcohol. So this is a diastereomer only because some of those configurations changed while some did not. And that's the main key that we're dealing with diastereomers. And then just to reference yet again, this molecule right here is just another perspective of the molecule I just pointed at. We just flipped it. So this one, they were diastereomers of each other. Perfect. And then we'll move on to our next example. So immediately, the first thing that catches my eye is going to be this alkene. Now, in terms of our alkene, what we can do to make sure that the atom connectivity may be a little different is we can start with our alcohol and see how close it is to the alkene. So for example, we'll start with this carbon right here, the one that is bonded to our alcohol, and we'll see how far away it is from the alkene. So our alcohol is 2 carbons away from our alkene. But if we were to move over to our rightmost molecule, we see that we have our alcohol right here, and it is only 1 carbon away from our alkene. Now, since we're going from 2 carbons away from the alkene to now only 1 carbon away from the alkene, this is a good sign of a constitutional isomer. And yet again, constitutional isomers have the same molecular formula, but as we can see, they also have different atom connectivity. Perfect. Sweet. And then moving on to our next one, yet again, we had to assess what the relationship between those two molecules are. And in this case, what I'm going to do, especially when I'm given just a molecule with one chiral center, I like aligning two groups with each other, similar to what we did earlier, and assessing those wedges and dashes. So what I want to do is I want to flip this molecule so that the bromines are in the same position and so that the hydrogen is also in the same position. So we'll go through and flip that over yet again, just like a book. And all we're doing is we're flipping it so we can think of the hydrogen as my thumb pointing down, and then my pinky, if I can do that, as the bromine. And as we're flipping it, we're moving that hydrogen up and then that bromine down. So we'll go through and show what that looks like. Oops. Yet again, the bromine will come down, the hydrogen will come up. And then yet again, just using a molecular model kit to show you guys what it actually looks like. We had this hydrogen facing down, and we had this bromine, which is purple, facing upwards. And this is yet again showing you what happens to those wedges and dashes. So we can think of this red group as our methyl group, as from your perspective, it's currently facing away from you. But if we were to take that bromine on top and then that hydrogen right here in white, if we were to flip it just like we did, that red methyl group is now facing towards you guys. So that's showing us yet again that those wedges and dashes have to flip whenever we plan on turning something over like the page of a book. So we'll go through and showcase what that looks like. Our methyl group is now wedged, and then our ethyl group, perfect, is now dashed. So looking at this molecule, to easily see and compare towards our other molecule, let's go through and drag and drop and see the comparison between the two. If we're looking at them, our hydrogens are in the exact same spot. Same with our bromine. They're in the same position as well. Both methyl groups are going to be wedged. Ethyl groups are dashed. And since everything is perfectly aligned, this means they are superimposable. And yet again, superimposable means we can perfectly align them on top of each other. And since we can do that, that means we're looking at the same molecules. So those molecules are what are called identical. You'll probably see that terminology a lot on exams, but these are just the exact same molecules, but different perspectives of them. Sweet. And then for our last question regarding stereochemistry in terms of seeing the relationship between them, we have this one. And this one's actually pretty interesting because looking at it in terms of like a first glance, we see that these bromines are currently wedged. But then if we look at these bromines, they are currently dashed. So your first train of thought may be, oh, since we flipped all the configurations over, they may be enantiomers, but that's actually not the case in this example. So let's go through, and yet again, we're going to flip this molecule over like a book, write down flip, and let's see what it looks like. Since we're flipping it over yet again, those dashes will turn to wedges. Include everything. And if we were to go through and drag and drop everything over, they are the exact same molecule. They are superimposable on top of each other. And this is a really good example, just to re-jog your memory from some of those OChem 1 concepts yet again. This is what's called a meso compound. Now, how do we know it's a meso compound? What we can do is show an internal plane of symmetry. So we'll go through, add that in, make a note of it. A lot to write down. Perfect. Sweet. If I misspelled anything, my apologies. But in terms of meso compounds, yet again, that's when we have that internal plane of symmetry. Now, what does that mean? Pretend you're just putting a molecule, sorry, not a molecule. Pretend you're putting a mirror right in a molecule. And in this case, our mirror will cut right through it. And since we have a mirror, this portion will be an exact reflection of the portion I just circled. So that's going to be our internal plane of symmetry, um, showing how they're going to be a meso. But we do have a question. What will make this compound an enantiomer? Really good question. So one of the ways in terms of if we were to go through this molecule, maybe change it around a little bit, what we could do is turn this wedged bromine into a dashed bromine. Now, by turning it into a dashed bromine, we break that internal plane of symmetry. And since we no longer have that internal plane of symmetry, that's how we could turn it into an enantiomer, if that makes sense. We'd have to go through some reactions in order to do that, but that's how we theoretically could. One thing I will note about meso compounds is that meso compounds do not have enantiomers. Perfect. And then just to make sure, did that answer your question? Perfect. Sweet. Alrighty. So from there, of course, we'll go ahead and move on. And up next, we're still going to be on the topic of stereochemistry, but we're going to go through assigning R and S configurations. And then just to do a brief overview in terms of the set rules we use, we'll use the Ingold Prelog system. And yet again, this allows us to assign priorities to either individual atoms or groups on a molecule. And then just to do a brief run through in terms of how we assign those priorities, if something has a higher atomic number, that means it'll have a higher priority. So just say if we're comparing a carbon versus an oxygen, the atomic number just showcases yet again the number of protons we have. So carbon has 6 protons, and then the atomic number of oxygen is 8. And since the atomic number of oxygen is higher, that means it'll have a higher priority. So that's kind of like the main thing we use to help assess priorities. But going into our next one, just say if a carbon is attached to a heteroatom, whether it's an oxygen, bromine, chlorine, iodine, whatever it may be, those will have a higher priority. And then in terms of our third thing we want to look for is just say if we're only dealing with hydrocarbons, correct? Say we have a hydrocarbon that looks like this, where we have a chiral center right here, and we're trying to assess priorities. This group will be a higher priority. We'll actually add in this just for fun. There we go. This group right here will be a higher priority than the one I just circled right here. And one of the ways we can assess the priorities with just simple hydrocarbons is looking at the number of hydrogens our carbon has. So for example, this carbon right here only has 1 hydrogen coming off of it, as opposed to this carbon has 2 hydrogens coming off of it. Now, since this group only has 1 hydrogen coming off of it, that's going to be higher in priority. And another way of thinking about it in terms of just hydrocarbons is the number of carbons this carbon is bonded to. So for example, this carbon is bonded to 2 other carbons, as opposed to this carbon is only bonded to another carbon. So this group will have a higher priority. And then also, if we're dealing with like double and triple bonds, those will also have a higher priority as well. And then in terms of a helpful tip to know, whenever we're dealing with assigning absolute configuration, whenever you have a hydrogen, those will always be the lowest in priority. So if we're looking at our next example, in terms of the next couple of molecules we'll be looking at, we need to find all the chiral centers, and we want to label them as either R or S. Now, one thing we need to remember about chiral centers is that they have four unique groups. So the main thing we have to do is just simply look at the molecule and ask ourselves which carbons have four groups. And the only carbon that's kind of sticking out to me so far is this group right here. We have a hydrogen, alcohol, then we have this large group, and then we only have a simple methyl group. So right there, we have four groups, which means it's a chiral center. Now, the next thing we need to do is go through and assign priority. And then after we assign the priority, we can figure out if it's R or S based on how the direction we're counting in. So like we just said, whenever we have hydrogens on our chiral centers, those will be the lowest priority. So we'll give that a priority of 4. And then in terms of our rules, we have to remember that when our carbon is bonded to a heteroatom, in this case oxygen, that oxygen has a higher atomic number, meaning it has a higher priority. So we'll give that number 1 priority. And then up next, we need to decide which group, I should say, has priority 2, and then which group has priority 3. And the best thing to do is to start at your chiral center and then just branch away from it and find the differences you have. So if we're looking at this group on the right, it's just a simple methyl group. But if we were to go off to the left, this carbon has a double bond, and it's also a lot more complex than it. And mainly because we have that double bond right there, this group will be our second priority, and then this group will be our third priority. Now, from here, like I mentioned, we need to count all of our priorities in order, and depending on the direction we count in, it'll tell us on if our configuration is R or S. So if we count in the counterclockwise direction, we'll be looking at the S configuration. And then if we're looking at the clockwise direction, we'll be looking at the R configuration. So in this case, let's go through and count our groups together. So we're moving from 1 to 2 to 3 to 4. And if you can see that direction, that is going counterclockwise. And that means our configuration is in the S configuration. Perfect. We'll move on. Sweet. So yet again, excuse me, for this molecule, we need to go through, find our chiral centers, and then from there assign priority. So looking at our molecule, we see that this carbon right here is chiral, as it has 4 groups. It has 4 different groups. I'll be more specific. We have a group here, here, bromine, and then this entire group coming off of that carbon. But let's look at this carbon more carefully. Now, at first glance, you may think it's a chiral center only because we're showing that wedged and dashed notation. But I will warn you, just because we're showing the wedges and dashes doesn't mean it's a chiral center. Only because if we go through and count the groups we have methyl group here, and then this dash group is a methyl group as well. So this carbon does not have 4 different groups, which means it is not a chiral center. So in terms of our pink chiral center right here, we'll go through, add in our priorities. Of course, bromine will be our highest priority because if we're looking at this pink chiral center and we branch off to the first atoms, this bromine has a higher atomic number. But what we can do from there is we can keep on branching. Now, in terms of this methyl group, we know that that will be our lowest priority only because if we look at these 2 other groups, they branch out a lot more. As opposed to the methyl group, it stops at 1 carbon only, so that's why it is our lowest priority. But let's keep on branching, right? So if we were to stop at this green carbon, in terms of us branching away from that pink chiral center, we see that those green carbons are both CH2 groups. So in order to assign priority, we need to keep moving through the molecule. And what we need to compare next is this carbon and this carbon. Now, one thing that catches my eye is that this carbon has no hydrogens, this carbon has three hydrogens, but most importantly, this carbon right here is bonded to an oxygen, which has a higher priority. So we'll go ahead and assign this group as our second priority, and then this ethyl group is our third priority. And then yet again, we'll go through and count all of our groups in order. So we're going from 1 to 2 to 3 to 4. And if I hold that there, we're moving in the counterclockwise direction, which yet again means we're looking at the S configuration. And I just wrote down R. We're looking at the S configuration. There we go. Perfect. We'll move on to the next one. Sweet. So looking at this molecule, we definitely have a couple more chiral centers. So if we were to go through and find them, we can first start off with this carbon bonded to our oxygen. And if we were to include our hydrogen as well, we can see that we have four different groups coming off of that pink chiral carbon. And then another carbon that's catching my eye is this one right here, that blue one, as we have four different groups. And yet again, what we can do is include that hydrogen. This is actually one thing I recommend doing, especially with absolute configuration, is that we have to remember with bond line notation, we always assume that hydrogens are there. So just make sure you draw them in, just so you're aware of if it's wedged or dashed. And then yet again, we have another chiral center, which is right here in red. And we'll go ahead and add in a hydrogen as well. And all, whether it's the pink, blue, or that red carbon, all of them are chiral because they have four different unique groups coming off of them. So we'll start with this pink chiral carbon. Yet again, hydrogen will be our lowest priority, so we'll give it a 4. And then in terms of the groups that this carbon is bonded to, we're bonding directly to an oxygen, which has a higher atomic number, which yet again gives it a higher priority. And now what we need to do is start at this pink carbon so that we can assign priorities 2 and 3. And in order to do that, we have to just branch through the molecule and find some differences. So if we start here and move one carbon out on each side, we see that this carbon and this carbon are both CH2 groups. But if we were to keep on branching, we move over to this blue carbon, but most importantly, we move over to this carbon, which has a double bond. Now, since this carbon has a double bond, that means this entire group is going to have a higher priority than this one over here. So we'll go ahead and showcase that with this side being our second highest priority, then this one up here being our third priority. And then yet again, we'll go through and count everything. So we'll move from groups 1 to 2 to 3 to 4. And if I leave that there, as of right now, we're currently counting in the counterclockwise direction, which we would assume would have the S configuration, but we have to keep in mind that our lowest priority should be dashed. So we'll go ahead and write that down. Lowest priority should be dashed. And if you remember, whenever we have our lowest priority in the wedge configuration, all we need to do is flip it. So like I said, we were counting in the counterclockwise direction, which would mean originally that we would be in the S configuration. If we were to just go through and flip that, we are now in the R configuration. Sweet. From there, we'll move on to the blue chiral carbon. Yet again, our hydrogen will be our our lowest priority. And then let's just keep on moving through the molecule from that blue chiral carbon. So if we move one carbon out, what really catches my eye is this double bond right here, as opposed to both our ethyl group and this carbon. They're just CH2 groups. So since this group has that double bond super close to it, that'll be our highest priority. And then in terms of our second and third priority, we keep on moving through the molecule. And if we're looking at this ethyl group, we have to remember that it's only two carbons, as opposed to this side of the chiral carbon branches out a lot and has a lot of different substituents. So that'll give us our second highest group. And then that ethyl group will be our third highest priority. Then from here, yet again, we'll go ahead and count everything. We move from 1 to 2 to 3 to 4. And if we showcase the direction, we are moving in the clockwise direction, which gives us the R configuration. Perfect. And then what was nice about that one is that our lowest priority was dashed, so we didn't really have to do any flipping or anything like that. And then we'll go ahead and finish it off with our red chiral carbon. So as always, hydrogen is our lowest priority. This oxygen right here will be our highest priority since it has a higher atomic number. And yet again, in terms of which priority will be 2 and which priority will be 3, if we branch on out from that chiral carbon, this group has a lot more branching, a lot more bonding, as opposed to this CH3 group. So this group right here will be our second highest priority, as opposed to the methyl group will be our third highest priority. And yet again, another way to compare it is that we have 2 hydrogens coming off of that carbon. We have 3 hydrogens coming off of this carbon. And whenever we have a carbon with a lower amount of hydrogens, that typically has a higher priority. So it's another way we can think of it. And then from here, we'll go through and count. We're moving from 1, 2, 3 to 4. Since we're moving in the clockwise direction, that gives us the R configuration. Sweet. And then from here, we'll go through and we'll start to talk about acid-base reactions. Now, the reason I want to talk about this briefly is just because these factors of stability will show up a lot in organic chemistry too. The main factors of stability we'll be talking about all fall back on that ARIO acronym that you may or may not have heard in OChem 1. And if you haven't heard it, it stands for atoms, resonance, induction, and orbitals. And it's also nice because it goes in order of most importance to least important. And in terms of atoms, the main thing we're looking for are, differences in electronegativity, and then also how large or how small an atom is. And then we're also looking at resonance. That's going to ask us, okay, are these electrons being delocalized? And if they are being delocalized, that means they're a lot more stable. Induction looks at the effects of any partial positives or even any partial negative charges that could have an effect with our stability. And then our orbitals, that's telling us, okay, which orbital is our positive or negative charge in? And in terms of acid-base reactions, we want to see where that negative charge is and which orbital it's in. So for example, if it's in an sp orbital, it'll be a lot more stable. But in terms of acid-base reactions, the most important thing to note is that a strong acid will yield a weak conjugate base, and a strong base will yield a weak conjugate acid. So if something starts strong, it will end weak. So from here, the first thing we want to do is define the most acidic proton in the following molecules. So looking at this, we have a couple different protons we could choose from. We have a hydrogen here, we have a hydrogen here, and then we also have the hydrogen on our oxygen here. And if we were to go through and draw out the conjugate bases, which I will copy and paste a little bit to make our lives easier. If we were to see the conjugate bases of all of those protons, we would have a negative charge on that carbon, one here, and then one on the oxygen. And then in terms of where I'm getting these conjugate bases, remember, when we have a base that steals a proton, the base will snag the proton, and then this bond between, for example, the carbon And the hydrogen, these electrons have to fall back onto the carbon. So that's where we're getting those negative charges from. And if we were to assess the proton, sorry, the negative charge that came from this proton right here, this is our conjugate base, and we don't really see any factors of stability. It's just hanging out on that carbon. But if we move on to our next proton and we were to look at its conjugate base, we see that the negative charge can actually be delocalized since there's a pi bond right next to it and it's being delocalized through resonance. So we'll keep that in mind that this conjugate base does have resonance. But if we were to look at our neighboring molecule, we have a negative charge on our oxygen, and that negative charge is right next to a pi bond, which means it can delocalize through resonance. Now, this is where it may seem tricky because both of these conjugate bases have resonance, but this is where us talking about atoms come into play, talking about electronegativity, right? We want that negative charge to be on the most electronegative atom in this case. And we're kind of battling between a negative charge on oxygens, because yet again, both can undergo resonance, and then one on carbon. So since there was a negative charge on carbon in this case, as opposed to a negative charge on oxygen, in both resonance forms with this conjugate base, that will be more stable, meaning this proton will be the most acidic. We'll go through the next one, get a sip of water. Perfect. So for this next molecule, yet again, we want to look for the most acidic proton. And the two main ones I want to look at will be the proton on this oxygen, and then also the proton on that oxygen as well. So we'll go through, draw out the conjugate bases. So the first conjugate base would have a negative charge on this oxygen, which yet again came from this proton over here. And then our other conjugate base would come from that carboxylic acid, which came from this hydrogen right here. And yet again, what we can do is kind of go through and assess the conjugate base stability. So if we were to look at this negative charge, we could show all the resonance, but there is a lot of resonance forms. But to sum it up, there would be a negative charge on this oxygen that can delocalize throughout this entire ring. So you might be thinking, okay, this negative charge has a lot of resonance. This one must be the most stable conjugate base. But if we were to look at this conjugate base over here, this negative charge can be delocalized through both of those oxygens. And this is a really important point to consider, is that the quality of resonance matters. So we'll write that down. Quality of resonance matters. And what I mean by that is where are we placing our negative charges? So if we're looking at this conjugate base, that negative charge is being spread on an oxygen and then a whole bunch of carbons with that ring. But if we're looking at the negative charge on this conjugate base, it's only being spread between two oxygens, which are more electronegative than carbon. So the quality of it is a lot better, which makes this proton way more acidic since its conjugate base is more stable. And then lastly, we'll look at this one. What I want to do in this case is we'll write down our hydrogens that we can steal from, or our protons. Here's a good contender, this one, and this one as well. And what I want us to do is internally ask ourselves, how stable is the conjugate base? So if we're looking at a conjugate base of this proton right here, this is something that we would have to do like maybe on a quiz or an exam in terms of that thought process, in terms of being efficient with the time. But just say if we had a conjugate base or a negative charge on this carbon, where would that negative charge be able to go? If we looked at the left side of the molecule, the negative charge can delocalize to this carbonyl over here. So from this proton, we can get some resonance, which is pretty good. Then if we were to steal this proton right here, we would end up having a negative charge on this carbon And the unfortunate thing about that one is that there's no real factors of stability. It's just a carbon, and we can't really delocalize it or anything like that. And then yet again, if we were to snag this proton right here, we would have a negative charge right here as a conjugate base, which could also delocalize into the carbonyl. But there's something special about this carbon. Now, if we're looking at what else that carbon is bonded to, the carbon is actually bonded to a bromine, and we have to remember those dipoles, right? So bromine is kind of stealing some electron density away from that carbon, and since it's stealing electron density, that carbon, get the pen out, that carbon actually has a partial positive charge. And if we were to have a negative charge from looking at that conjugate base, the negative charge not only has resonance, but it has some inductive effects. And since we have that partial positive charge close to that negative charge, that makes it more stable, meaning that this hydrogen is the most acidic proton. And then actually there's one more what we can do. Yet again, we can draw out those conjugate bases. And we need to first realize which hydrogens we could steal. We could snag this one, we could take this one, or we can take this one right here. And then what we can do is draw out the conjugate bases. Copy and paste the cheat a little bit. Sweet. And then tools are all over the place. Sweet. So now what we have to do is assess the conjugate base stability. Now, if we're looking at the conjugate base that came from this proton, which is right here, we would have a negative charge on our carbon. And this negative charge is right next to a pi bond, so it can be delocalized through resonance, which is good. And then if we're looking at this conjugate base, which came from this proton right here, we don't really have any factors of stability really for this negative charge, or at least of any importance. But we have this negative charge right here, which is right next to that pi bond, so it can undergo resonance. But let's go ahead and actually draw out that nitro group. So a nitro group, if you remember, has a double bond to oxygen and a single bond to oxygen, which has a negative charge, and that nitrogen has a positive charge. And this can undergo some good resonance, where we drop those lone pairs down to form a double bond between carbon and nitrogen, and we'll kick a lone pair back onto oxygen. And if we were to showcase that resonance form, we would get something that looks like this. Right here is a good introduction into resonance. So since we have a negative charge, well, or at least we can push that negative charge up onto an oxygen, that's going to help stabilize our conjugate base a lot more. And since this one, that conjugate base, is the most stable, that means this proton is the most acidic. Sweet. And then up next, we have of the molecules shown, we want to circle the strongest base and we want to label Y. Now, in terms of something acting as a strong base, we have to consider its lone pairs, right? Because the lone pairs will be doing the attacking. So we'll add in our lone pairs, and we want to see how those lone pairs can move. Yet again, this will be a good introduction into resonance because we want to see if those lone pairs are either localized or if they are delocalized. So if we are looking at these lone pairs, they are currently localized onto that oxygen. But if we looked at these lone pairs on the oxygen, those can undergo resonance with the entire ring right here since we're surrounding it with double bonds. So we'll undergo a lot of resonance right here, which means those lone pairs are more stable as opposed to these lone pairs are localized, making them less stable. And then these lone pairs, to kind of put more there, it'll be delocalized. So since these lone pairs are a lot more stable, since they are delocalized, it will be less basic as opposed to these lone pairs, since they are localized, they don't really have any stability going for them. It's going to be more basic. It's going to want to react. So this will be our strongest base only because those lone pairs are localized, making them less stable. Nice. And then from there, we'll go through and kind of dive right into resonance. So, as a brief recap in terms of just what resonance is, it'll be the delocalization of electrons in the pi system. Now, in terms of the big three rules of resonance that we have to follow, number one will be resonance forms will always have the same atom connectivity. So what that means is that we are not moving our atoms around, but instead we're moving electron density, and we showcase that by using the curved arrow notation. And then the second thing we want to look out for is that resonance forms have the same net charge. So just say if our original resonance form starts with a negative charge, that means every single resonance form we make also needs a negative charge. And then lastly, resonance only occurs in the pi system. And in the pi system, we'll be looking at pi bonds and then lone pairs that are moving and weaving through those p orbitals. And yet again, pi system, just to recap what that is, because it will be super important for organic chemistry too, is the pi system looks at electrons that flow through p orbitals. And that's, like I said, that'll be the main basis of resonance using p orbitals. And then in terms of drawing resonance forms, the main thing we want to start with is electron density. So find your charges or find p orbitals or lone pairs and try to move those where you can. And then lastly, we'll review what the MRC is. And MRC, yet again, stands for the major resonance contributor. And there's going to be three main things we want to look out for when it comes to the MRC. So the first thing will be looking for the greatest number of filled octets. Now, for it to be major, for that resonance form to be decently stable out of all of them, it needs an octet, meaning our atom needs those 8 electrons surrounding it. In terms of our second best thing we can look out for is we want a resonance form with the fewest number of formal charges. So if we have a neutral molecule where the resonance form itself shows no charges, that'll be the one we want to go for. And then lastly, we want to see where those charges are. So for example, if we're looking at, a resonance form with a negative charge, we want that negative charge to be on the most electronegative atom. And then if we're looking at resonance forms with a bunch of positive charges, we want that positive charge to be on the least electronegative atom. And then one thing I will note, just so you guys don't forget, a positive charge on a carbon means it is a carbocation which lacks the octet. So as we're looking at some of these resonance forms, we can't forget that a positive charge on carbon means it's missing its octet and it's not filled, which is not good. So from there, we'll kind of just dive right into our resonance structures. And we'll try to work slowly through them. If you do have questions, please feel free to put it into the chat because this will be a very important topic in terms of organic chemistry too. But like I mentioned earlier, we want to start with our electron density. And from there, we want to see how we can distribute and delocalize that electron density. And just to do a little bit of a deeper dive, picture it this way. If you had a whole bunch of negative charges super close to each other, that is going to repel each other because it is very unfavorable. But if we want to make those electrons happy, because those electrons don't want to be super close, we can help spread them out and delocalize them, which is kind of the goal of resonance. So yet again, we'll start with our electron density. And remember, our electron density in terms of resonance can only move through the pi system. So since we have our negative charge here, and we have a pi bond right next to it, we'll go through and we'll move our negative charge towards that pi bond. It's actually going to drop down to help form a double bond. And then since we're forming a new double bond between these two carbons, This carbon right here, we have to remember, is bonded to a hydrogen. And if we were to just show that double bond right there in purple, this carbon has 5 bonds, which it does not want. It only wants 4 bonds. So what we can do to make carbon happy and to maintain 4 bonds, as we're dropping these lone pairs down to form a new double bond, we can actually kick these pi electrons back up to form a lone pair. We'll go through and showcase what that looks like. So we have our new double bond right here. Then we have our other double bond over here. And then we have our new lone pair, which we just kicked up back onto this oxygen. And then if we were to keep assessing the molecule, right, we have our lone pair right here on this carbon, our negative charge. And yet again, we want to see how far we can push that negative charge through the molecule. So this negative charge is right next to this pi bond right here, and we can do exactly what we did. We can drop that lone pair down, our negative charge, to help form a new double bond, which while we're doing that, we can then push these electrons from our pi bond back up to form a lone pair. Go through. So we have our pi bond from there, our new pi bond that we just formed, and then right here we have our new negative charge. Now, if we were to keep on going, let's say if we're looking at this carbon, we would not be able to undergo resonance only because there's no p orbitals right here. This carbon, if you remember, that is sp3 hybridized, and since it's sp3 hybridized, we lack any p orbitals for those lone pairs to move into. And one other thing with this question is I want us to try and find the major resonance contributor for all the resonance forms we draw out. Now, this one's actually kind of tricky, only because there is no major resonance contributor, because all of them will be equal in energy. Only because the negative charge will be on carbon only, and because it's on the standard carbons, there's no major resonance contributor, so no MRC. And that'll happen sometimes. If you have the negative charge going on the same atoms, it sometimes aligns up to where all of them will be equal in energy, which means there's no major resonance contributor. So equal in energy. Perfect. And then we'll move on to the next one. Sweet. So in terms of resonance forms, whether it is a negative charge or a positive charge, like we saw in this example, right? We wanted to start with our charge and we wanted to see what we can do with it. And more specifically in this example, we started with our electron density and we wanted to see how far and how much we can push it throughout the molecule. But in this case, we are starting with a positive charge. Now, we always want to start with our charges, but we also want to start with the electron density. So we know that a positive charge means we lack electron density, but what do we have over here? We have a pi bond which has electron density. So let's try to move that electron density from the pi bond into that positive charge or towards it. So we'll go through and move one arrow on down to form a new pi bond. Through and draw out our cyclic structure. So right here will be our new pi bond. And remember, if we're moving electrons away from this carbon, that means this carbon will now have a positive charge. And we'll go ahead and add our OH group up here. And when it does come to positive charges, a helpful trend, I will say, is that whenever you start with the positive charges, when you start with a positive charge, you will only have to move one arrow. So we'll write that down. And that'll be a common trend we'll see when you start with a positive charge and you're moving those pi bonds. Sweet. And then yet again, we'll assess our positive charge Do we have any more electron density close to it that we can move towards it? We do. We have this pi bond over here, which we can go ahead and move towards that positive charge. And by doing that, we now create a new positive charge and a new pi bond. Perfect. And then we'll go ahead and include our positive charge. And from there, it might look like we're all done, only because if we're following the trend that we've been doing, we have no more pi bonds next to our positive charge, but we do have some electron density still. If we were to look at this oxygen, we can't forget that we have lone pairs on the oxygen, and the lone pairs on the oxygen can actually dive down, go towards that positive charge, and from there, we now create a new carbon-oxygen double bond, which will actually give oxygen a positive charge. Now, in terms of the major resonance contributor, if we're looking at all of these resonance forms, there's one that really sticks out, and it's this one right here. Only because if we're looking at these three resonance forms, all three of them have carbocations, and yet again, carbocations lack the octet. As opposed to here, the oxygen still has a lone pair, and it has three bonds, so it still has the octet, which means it's happy. So this will be the MRC, as it has a full octet. Perfect. Sweet. And then we'll just keep on moving along. Now, for this next example, yet again, we're going to start with our charges. More specifically, in this one, we have a negative charge. So let's see how much we can delocalize that negative charge. In this case, we have a negative charge, yet again, right next to a pi bond. So let's try to move those electrons towards the pi system. Those electrons drop down, form a new double bond. Then these electrons from our pi bond will move up to form some lone pairs. Perfect. And now we have a negative charge on this carbon, and we can keep moving with it. If we were to keep looking at what's around that negative charge, this negative charge is right next to another carbon-oxygen double bond. And since it's next to a pi bond, we can undergo resonance again. We can move this negative charge on down, form a new pi bond, and then we'll be moving these electrons between that pi bond up to oxygen. Sweet. So those are our resonance forms. And yet again, what we have to do is try to find the major resonance contributor. Now, all of these have the octet, and a lot of the times, whenever you're looking at resonance forms with only negative charges, and you're trying to decipher which one is the major resonance contributor, a lot of the times it'll fall back onto electronegativity. Now, if we were to assess where our negative charges are, we have a negative charge on nitrogen, carbon, and oxygen, and out of those three, oxygen is the most electronegative, so it'll better hold on to a negative charge, making this resonance form the MRC. And that is due to electronegativity. Sweet. Then we'll move on to another one. Now, in this case, right here is a good example of what I was talking about earlier, that whenever we start with charges or whatever it may be on a resonance form, we always want to have the same net charge. So even though we have a negative charge and a positive charge, together the entire molecule would be considered neutral. So that means every single resonance form we draw, it should be neutral overall. And in this case, like we mentioned, we always want to start with our charges, and also we want to start with the electron density. So the goal for this one is to start with our negative charge And let's see if we can push it all the way down to that positive charge to help delocalize it. So since we have a negative charge up here on the oxygen, we'll go through and drop that on down, only because it is right next to a pi bond. So we'll drop those down. And by doing that, we have to kick the electrons from this pi bond up to nitrogen. Draw our structure. Oops. Perfect. Whoops. Jeez. There we go. Sweet. And then from there, we still have our negative charge on our nitrogen. Yet again, let's look for nearby pi bonds. We still have a pi bond right here, and I forgot to... Perfect. Sweet. Yeah, so we'll keep that negative charge. I was just checking the formal charge and everything. My apologies. But yes, we'll have this negative charge. We'll drop it on down since we have a pi bond right next to it. And then since we're dropping these electrons down to form a new pi bond, we'll be kicking the electrons from this pi bond up onto oxygen, giving it a new lone pair. And by doing that, we actually notice something, is that if we're giving oxygen a new lone pair, it actually helps neutralize that oxygen. And a matter of fact, it'll help give the entire resonance form no charges, which is quite nice. And since this resonance form has no charges, it'll be our major resonance contributor. No charges. Perfect. And then for our last resonance example, for this one, yet again, we're starting with our positive charge, but we also have to start with electron density. So we'll start with our pi bond because that has electron density, and we'll move it towards our positive charge. Move it over like that. And yet again, since we're dealing with just a positive charge on its own, we only have to use one arrow. That's a common trend. So we'll go ahead and draw out our structure. Have our new pi bond right there. Positive charge here. Other pi bond. And then as we keep on working through it, yet again, our positive charge is right here. So let's look for any nearby electron density. We have a pi bond over here, and we can still move it towards that positive charge. Just like that, using our one arrow. Oops. And if we were to look at our resonance form, this is what we're left with. Sweet. Now, in terms of finding the major resonance contributor, this one might seem a little tricky at first, only because each individual resonance form still has a carbocation. And how do we know factors of stabilities with carbocations? It all comes back to hyperconjugation, if we remember what that is from OChem 1. Basically, as a brief overview, hyperconjugation is looking at, how many sigma bonds, more specifically alkyl groups, are surrounding that carbocation to help kind of donate electron density. And mainly, whenever a carbocation is on a tertiary carbon, that's when it's most stable. So that'll make this one our MRC, our major resonance contributor, due to hyperconjugation. Perfect. We'll keep on moving. Nice. So we're done drawing the actual resonance forms, but this is showcasing how resonance will be applied in organic chemistry too. So right here is a really good example. And in terms of finding the electrophilic sites, which is what we want to do, this is something you'll be doing at, I would say the last third of organic chemistry, but it's something you can still do now. So what I want us to do is to go through and to find those electrophilic sites on the molecule. And if you forget what electrophilic means, that for example, means we are lacking electron density. And in this case, we can just think of it as partial positive charges on the molecule. And what we can do is work through the individual resonance forms. So if we're looking at the electrons in this pi bond and we wanted to showcase a resonance form, what can happen is the electrons in that pi bond can fall back onto oxygen. And if we were to showcase what that looks like, let's draw out our structure. We would have a negative charge on our oxygen because those electrons are falling onto the oxygen. And then we'll have a positive charge on our carbon. So that's one of the resonance forms we can have. And now, since we have a carbocation here, right next to a pi bond, we can still showcase resonance, have that pi bond move over, and from there we get a new resonance form where we still have a negative charge on oxygen, but by doing that, we now have a partial positive charge on that carbon. So by looking at those resonance forms, wherever we have a positive charge on one of the individual resonance forms, that's showcasing where we have those partial positive charges on our molecule, which means we would have a partial positive charge on that carbonyl carbon, and then a partial positive charge on that carbon right there. Perfect. Then moving on to our next example, we want to see which alcohol, we want to explain why alcohol A is more acidic than alcohol B. Now, what we can do is draw out the conjugate bases and see any factors of stability we have. And in this case, we still have a negative charge on both oxygens if we're looking at both conjugate bases, but more specifically, these nitro groups moved their positions on our ring. So we'll see by how moving those positions on the ring, how it can affect the basicity of it. So if we were to go through and showcase the resonance forms, a negative charge can drop down, kicking the electrons from this pi bond up onto that carbon. And by doing that, we would get a resonance form that looks like this. And if we remember back to those nitro groups, whenever we have a negative charge next to a nitro group, that has a lot of resonance along with it. So we'll keep that in mind. And then let's go through and look at the resonance with this one. Negative charge will drop down. The pi electrons from this pi bond will fall back onto carbon. And by doing that, we would actually get a structure that has a negative charge on the same carbon, but our nitro group, yet again, is on a different position. And if we were to go through and still showcase our resonance forms, negative charge will drop down, electrons from our pi bond will fall back onto carbon, and then we would get something that looks like this. Where our negative charge is no longer on the carbon with the nitro group, it's now at a carbon that's away from the nitro group. So the reason alcohol A is more acidic than alcohol B has to do with the stability of the conjugate base and how we can move the negative charge up to the nitro group, which we can do right here since that negative charge is next to the NO2 group, as opposed to this one over here, we cannot get a negative charge on the carbon with that NO2 group, so we lack that extra stability. Perfect. And then we did an example similar earlier on, but yet again, this is just showcasing how resonance will help describe stability and reactivity, and we want to see which lone pair is more basic. So we have a lone pair on this nitrogen right here, and then this nitrogen right here as well. And let's see how those nitrogens interact with the pi systems. Now, if we're looking at the lone pair on this nitrogen, it is right next to pi bonds. And since it's directly next to pi bonds, it can still undergo resonance. It can drop down, and we can showcase those individual resonance forms. And more specifically, if we were to look at where that lone pair is, it can be in a p orbital. So we'll point that out. But in terms of our other lone pair on this nitrogen right here, even though there is a pi bond right here, that double bond, the lone pair cannot participate in resonance. Now, if we were to showcase which orbital that lone pair is in, it is actually in an sp2 orbital. And since that lone pair is not in a p orbital, that means it cannot undergo resonance, which means we lose some of that stability. And just to kind of go over why it's in an sp2 orbital, yet again, if we were to look at the hybridization of that nitrogen on its own, it's currently sp2 because there's 3 electron groups. And since it's sp2, that means it's leaving behind a p orbital, but that p orbital is being used in this pi bond right there. And since that p orbital is being used, that means this lone pair has to be in an sp2 orbital. So yet again, in terms of being more basic, that means our lone pair has to be less stable, and this lone pair on our nitrogen is less stable, making that entire molecule more basic. And then for our final question, what I want us to do is to provide a mechanism for the following reaction. This will be a good introduction for next week's topics, as we will be talking a lot more about those reactions. But in order to solve this, we need to find our nucleophile and we need to find our electrophile, which in this case is easy only because we are shown a negative charge right there. So this molecule will be our nucleophile, and then this molecule will help us, it'll be our electrophile. And if we're reviewing those alkyl halides, which is what we have right here, our electrophilic site will be this carbon right here, right? Because it does have a small dipole due to that bromine. And if we're looking at the product of our reaction, we have we have a 3 carbon chain right here. We're on carbon 2, it's bonded to an oxygen. And then we have 3 carbons where carbon 2 is bonded to an oxygen. And then from this carbon, we're adding 2 more carbon groups. So looking at it, that's telling me that this was the new bond we formed right here. And that if I were to highlight some carbons just so we know what's attacking, it's showing us that this carbon right here attacked this carbon right here to form our new double bond. And in terms of where these 2 carbons came from, that came from our alkyl bromide. And it's telling us that this carbon is nucleophilic. Now, how do we know it's nucleophilic? Yet again, we can use resonance. So let's go through and showcase the resonance forms on this structure. So if we have a negative charge on that oxygen, if we're looking at the resonance forms, that negative charge can drop down. And by doing so, it forces the electrons from this pi bond up onto the carbon, which gives us a resonance form that looks like this. So by showcasing those resonance forms, we see how that carbon can be nucleophilic and where that negative charge comes from. And overall, if we were to showcase a mechanism for the reaction, we'll go ahead and draw out what's called an enolate. Draw out our arrow. Perfect. So what we can do to showcase the mechanism, more specifically how we can make this carbon nucleophilic, right? We can do this all in one step, where we have the electrons from that oxygen drop down as if we're showcasing a resonance form, right? And then these electrons in that pi bond will be our nucleophile. And more specifically, they'll be associated with this carbon, and you can think of it as a negative charge on the carbon. So it'll go through and it will attack our electrophilic carbon. And by doing that, remember, whenever we're attacking something with a leaving group, we have to kick out our leaving group. And then from there, we can show our final product. And then there we have it. So yet again, that's just a really good example of how we can use, our knowledge on resonance now to showcase some of the more complex reactions we'll be learning a little later in OChem 2, only because the reaction we just covered, we can do that now, but that's not a reaction you'll learn until probably the last third of organic chemistry 2. And then one last thing I'll note in terms of resonance is that if you're ever stuck with a reaction, whether it's at the beginning of OChem 2 or even at the end of OChem 2, if there's pi bonds and negative charges, try to use resonance to help you describe the reactivity. And then that is it in terms of this week's tutoring session. I'm happy all of you all joined. And in terms of next week's tutoring session, to give you all a recap, we'll be going over a lot of those OChem 1 reactions, and then we'll also do a dive into a synthesis review, just so we're primed for a lot of the new reactions we'll learn in OChem 2 together.
Thank you so much, Cooper. That was fantastic. I hope this was helpful to everybody. I'm going to put in the chat right now what I recommend going over again. That was that category. So if you feel like after this, oh man, you need to review resonance, or if you want to get a jump start on looking over your OChem 1 reactions, go ahead and click that link. You'll see that, and that'll help you for next week. We're also going to send out an email letting you know the times, and it's actually it's the same exact time, and it's going to be on a Wednesday. Most specifically, we're going to tell you what we're going to go over. So what Cooper is going to go over, we'll send that PDF. And yeah, I can't wait for you guys to keep understanding and keep reviewing all of this. And I hope to see you next time.
Ooh.
See you guys.